So, good afternoon, ladies and gentlemen. Welcome to the afternoon session. My name's Nick Thomas. I'll be the moderator, the chairman for this session this afternoon. And it's my great pleasure to introduce first Professor Günther Hasinger, who's the current Director of Science of the European Space Agency. Günther has a remarkable record over the past 30, 35 years, I suppose. I ought to be quiet about that. But he's been director of the X-ray and gamma ray group at the Max Planck Institute for Extraterrestrial Physics in Garching. He was also scientific director of the Max Planck Institute for Plasma Physics. And he actually is used to this type of weather from his previous job, which was as director of the Institute for Astronomy in Hawaii. And he's now going to give us a presentation about ESA's plans for the future. Günther, it's all yours.
Thank you very much. It's a great honor and great pleasure to address you here in this historic symposium. We had already a wonderful morning, and I can actually pick up where Pascal left this morning. It is going almost seamless into the rest of the universe. But for us at ESA, you know, we do not only have the science program, we also have the exploration program, we have Earth observation, and in principle, science is everywhere. And when the DG is asking some scientific question, he always looks at me, and I cannot answer all the questions, but I try to encompass as much as possible. In particular, as you know, the scientific program of ESA is a mandatory program, which is funded by all member states in the same proportion. And so we are very lucky because it gives us a very long-term planning perspective. The exploration program, which is kind of joined at the hip with us, is an optional program, a more top-down planning program. And so there are interesting synergies, but also interesting tensions between those two programs. I will start with the fleet of ESA in the astrophysics arena, and then I come to the fleet in the solar system. Nothing to compare with Thomas Zurbuchen's 106 missions, but we still have quite a number of missions which we are working on. And we have in this chart separated them out as a function of time. And I always say we are standing on the shoulders of giants, and the giants are actually sitting here in the audience. They are basically responsible for all the missions that have already been so successful over the first 50 years of ESA. And it started here, together with many other activities, but CERN was really one of the founding functions of the European space. And we currently have these 4 missions in space. Our working horses are a very strong partnership with NASA on Hubble. Gaia is right now really turning the world of astronomy upside down, and then the 2 high-energy missions. But I'm very happy to say that we are preparing quite a number of missions currently building. And the first one that you will see flying is Cheops this year, which is led and built here in a partnership with ESA. And then we will launch James Webb Telescope. We will have several other of these. And actually my dream, and I will spend a little bit of time today here, our 2 flagship missions, LISA and Athena, which are in particularly focusing on the strong gravity and black holes. I would like to fly them together so that they can observe together, and I will come to that in a minute. But let me come to the ESA fleet in the solar system, again, similarly organized, a very strong legacy with Rosetta, Cassini, Huygens. This is really cool stuff. And in particular, as you know, Rosetta had a very, very strong influence from currently we fly quite a number of missions, but they are mainly concentrated in the inner solar system. We have launched Bepi Colombo in October last year, and I dwell a little bit on that. And again, we are preparing quite a number of new missions, in particular the big flagship mission JUICE, which will go to Jupiter in 22. And again, one of my dreams here is to find money for an ice giant mission that we could do together with NASA. There's a unique celestial opportunity coming up in the end of the 20s, early 30s, where Jupiter is standing in front of Uranus and Neptune, and you can get gravity assist to Jupiter. And so if we want to do it, we have to do it now, and that is a very important push for your generation, for the young generation. So let me show the textbook launch of Bepi Colombo. Several of us were in Kourou at that time. It was my first ESA launch, and I was really biting my nails, and then I was extremely excited and happy when everything went nominal. Everything went nominal, which means a huge engineering feat, tens of years of technological development. And it's very nice to see that several of these new technologies, like for instance solar electric power, but also the solar arrays and so on, are completely new technologies which are now already used in other missions, in telecommunication satellites and so on. Just in passing, I would like to remark that the selfie cameras that Bepi Colombo is carrying and that are photographing itself all the time have been made in Switzerland. So they are giving you the movies from Bepi Colombo on its orbit, 9 million kilometers in 7 years before it finally reaches Mercury. And that brings me to the solar system. As Pascal already has shown you, the solar system is not just poor 8 planets that we have, but it consists of much more stuff. It's actually showing the rubble pile of the construction phase of our solar system. And this is a beautiful picture which has actually been put together by a biology student. She is usually making pictures of creatures, and she used the solar system as one of the arts concepts. And you see all the asteroids around the planets. You see the Kuiper belt. What is missing in that picture is the Oort cloud. The Oort cloud is the place where we believe that there is primordial material from before the solar system was actually forming. And you know, the comets are coming out of the Oort cloud. What we have announced last week is a new mission which is actually trying to catch one of those comets that has never been there in the solar system before. So it still has to be discovered. It's not yet known which comet we will observe. But we are flying a mission to L2, which will wait there until the right comet is coming by, and then it flies to that comet to intersect it and to do studies of that. If we are lucky, it could also be an interstellar visitor like Oumuamua, which we are also expecting a 30% chance that we could actually intersect an interstellar visitor. And that shows, I mean, the first interstellar visitor was discovered 2 years ago, and now we already have a mission approved, or selected at least, which will go there. This is the silver sailor, the silver surfer, which is surfing to that comet. And what I want to point out is it is a very young team of scientists that came up with this idea. It's spread all across Europe, but it also has contributions from Bern. There's a Bern element in this mission. Now I want to move a little bit further out, and I want to travel with you through the Milky Way. We want to go to a few other important places in our galaxy. And those of you are all astronomers, you probably have identified the constellation here, Orion. And we are now flying in the direction of Orion, and we will see that the sky becomes alive, and that the stars are only projections on a stellar sphere, but on the celestial sphere. We are now flying past the Orion Nebula, and we are flying past the Horsehead Nebula. This film actually has been put together by Brent Tully in Hawaii, so that's why I like it so much. Another stellar nebula, a star formation region. And then we are passing by soon at the Crab Nebula, which I have made my PhD thesis on, probably one out of 250 PhD theses. And there was just a recent, last week, a press release that they have found the highest energy photons from the Crab Nebula that have ever been found, 450 TeV photons, which is unbelievable. Okay, this movie goes on, but I have to stop it here because I don't want yet to go to the extragalactic realm. But just 2 weeks ago, we celebrated the 10 years anniversary of Herschel and Planck. And look at these beautiful, colorful pictures of Herschel with all the cold dust and gas, and with all the different colors, different temperatures, different composition. And I wanted to point out, this is the Horsehead Nebula here. And so this is what the Hubble Space Telescope observed in great detail, together with the Eagle Nebula. And the stars are formed in these cocoons, which are basically blown away from the strong winds and the strong radiation from the bright stars in the vicinity. And that brings me to the Orion Nebula. These are relatively classical, relatively old pictures already, but I just want to give them as a bridge. The Orion Nebula, when you look at it with the Hubble Space Telescope, is fascinating. It has these 4 bright O stars in the center, which are blowing away all the other stars. When you look at it in the infrared, then you see roughly 1,000 young stars in that nebula. And this is the strongest star-forming region. And that is the place where we can really see the creation of new planetary systems, which has been discovered by Hubble first. You see these shadows of disks around stars. And in 2 cases here, for instance, you actually see the ring of the disk. You see the jet that comes out of the star. And you also see this kind of tadpole shape that is from the winds of the O stars that are blowing away the shock around. And we have already seen this morning, and Ewine, I think, will clearly point to that again. Now we have the capability to look at these disks in great detail. And Alma is really showing us the place where the planets are created right now. So these holes here in the disks are where we believe the giant planets are formed. Brian Schmidt this morning has already related to the TRAPPIST system, and I wanted to show you, and sorry Thomas that I steal the NASA presentation here, but that is a wonderful Spitzer data set which looked at this TRAPPIST-1 system for 500 hours. And which actually was the one who identified the 7 planets. The European paper from Brussels originally had 5 planets, and then it turned out that 5, I believe, that one was actually a double planet, and so the new data showed this beautiful system, which is not very much larger than the Jupiter system. If you take Jupiter and its moon, this is roughly the size of the system. It's a red dwarf star, and this is the Spitzer data where you beautifully see every individual dip when one of these planets is moving past. So this is really the great art or the industry of using transits for studying and finding exoplanets, and this is what Willy Benz will do with Cheops to observe these eclipses, these transits with much higher accuracy and then determine physical parameters of the objects. But I wanted to show this again. So if you compare the TRAPPIST-1 system to the solar system, and this is 25 times enlarged, so in actual it is not very much larger than the Jupiter system, but you also have the habitable zone, and you can show that at least 3 of those planets are in what we formally call the habitable zone. And so the big question is, are these really habitable? I mean, it is much easier to find Earth-like planets around M dwarfs than it is to find a real Earth-like planet around a solar-type star. And so the question is, are these, could these be analogs, so to speak, of places where we would like to go and maybe even live? And so what the Hubble Space Telescope has been able, with transit spectroscopy, Hubble was able to take spectra of 3 of these planets. And Hubble actually found that if there would be hydrogen atmospheres, you would have huge spectroscopic features. Hubble did not find any features, so they can say it's either rock, it could be water, but it could also be something else. And the problem is that these small dwarfs, these red dwarfs, are very active stars. They rotate very fast, they create huge magnetic fields, they create a lot of X-ray emission, UV emission. And so we have, for instance, observed some of these stars. This is Proxima b, and this is the TRAPPIST system. We have observed it with XMM Newton, and you see huge X-ray flares, which will make life not easy in these planets. But there is actually an interesting paper that came out 2 years ago. If you have planets which run around in a stellar magnetic field which is so strong, the star magnetic field will actually induce a current in these planets, or can induce a current in these planets. It's pretty much the same way that the induction fields in the kitchen, in our kitchen ovens are working. And it's likely that these planets are actually heated from inside so that they have liquid lava surfaces. So it's not a good place to go there first. I think we really need to find an Earth-like planet, a real Earth-like planet. And Plato is probably the first mission that can find real Earth-like planets, because you have to observe for 4 years in a row in order to see an orbit of 1 year, and you want to have 3 transits in order to identify that it's a true orbit. And so you need a very, very long baseline, and Plato will do that. Nevertheless, the Kepler harvest and now also tests coming in is really extremely impressive. And what you see here is the orrery, the clockwork of all these Kepler planets that have been discovered throughout the Kepler mission. And it's very interesting to look at them. First, there are many large planets which are pretty much the size of Jupiter. And then there are also many hot planets which are very hot, 1500 degrees or something like that. There are no real solar system analogs. If you think about this is the solar system, this is Jupiter orbit, this is Saturn orbit. They are all much smaller. And the reason why they are smaller is because the observing time is much shorter than what you need for the solar system. And so there is really the holy grail of the future, maybe 10, 20 years, is to find a real Earth-like system and a solar-type sun around a star and an Earth-like planet around it. And this is hopefully done with Plato, and then it will be followed up with all the power that we have with the ELTs, with the James Webb Telescope, as we have heard this morning from Xavier Barkons. So, but the very interesting aspect that we learned from all these planets is that most of the planets in the universe are actually nothing like our solar system. They are either super Earths, they are about 2 times the size of Earth, or mini Neptunes, about half the size of Neptune. And if you sort the planets of the solar system in this sort order, then you see there's a big gap between Earth here and Neptune. And most of the planets which Kepler sees are actually in between these two. And so this is actually a strong motivation. We know a lot about Earth. We know almost nothing about Neptune. So this is another strong motivation why we want to fly to Neptune or Uranus to really learn how these planets are formed or what they are consisting of. Okay, and that brings me to Cheops. We are really all looking forward, together with Willy as the PI, to the launch later this year. The launch window starts on October 15th. Then Cheops will observe all these known transits, hundreds of them and a few hundred stars, and will characterize those planets, will measure the sizes, but can even do something more, like, for instance, measure the slope of the ingress and egress to say something about the atmospheres and so on. It will be very exciting. And Cheops is actually the first one of a whole slew of exoplanet missions that ESA has already decided. Plato will follow soon, and then we have decided last year to also select Ariel. Ariel is a spectroscopic mission which will then take spectra of all these exoplanets. And if there is something like a Hertzsprung-Russell diagram, then Ariel will hopefully find it. And that is a very important ingredient in understanding the whole zoo of exoplanets. Just a few weeks ago, we waved goodbye to Cheops in the clean room of the Airbus company in Spain. And I would like to give a strong compliment to the whole team. This is the first ESA mission that has been built in budget and under schedule. Hopefully. It's not the first, but at least, sorry, Roger. No, I should never have said it, but it has been built. It has been built under budget and under schedule, which is very important in these times. There's, as I said, a bright future, a glorious future for exoplanets in ESA, and in particular also for the ones which we will then pick out, the golden planets that will be observed with JWST. So now let me come to our hero, currently Gaia. Gaia, as I said, is really turning astronomy upside down. It changes completely the foundation for astronomy. It's finding so many exciting results that you really shake your head. It's flabbergasting. Every day there are about 3 papers published on the most recent Gaia results. And I want to point out a few of those. But I would also like to point out that Gaia now is the basis of all navigation systems. I mean, whether it's the celestial navigation system or the terrestrial navigation system, because you need accurate stars in order to correlate your positions against the rest of the universe. So Gaia is the new frame of reference. But apart from that, it is also a wonderful discovery machine. And so here you see the Milky Way unrolling from the Gaia data. Every little point is 1 star. And then the data release that we did in April last year, it also giving colors to the stars so we can see which of the stars are red, which are blue. And we have published 1.7 billion positions of stars, but 1.3 billion colors of stars. And so you can imagine with 7 billion people on Earth, every 5 of you can basically share one star. So that's quite a number. But very important among the Gaia data set are the stars where we do not only know the position and how they move on the sky, but we also have the third dimension, so we get the velocity in 3 dimensions. So it's a 6-dimensional parameter that is needed to really trace back where the stars came from and then do galactic archaeology to see what the fate of these stars was. And there's a very exciting result that was published last year in Nature by Amina Helmi, where out of the 7 million Gaia stars, which have all full velocities, 30,000 seem to move in a completely wrong direction. So most of the stars are moving more or less around the Milky Way, nice in a circle, but there are 30,000 stars, and they are shown here in these yellow arrows, which seems to crash through the Milky Way somehow. And they are also, some of them flow in one direction. No, I think most of them flow in this direction. And this has been interpreted as the result of a merger of our Milky Way with another galaxy. So there was another galaxy coming through, and these red stars that you will see here down is actually this other Milky Way, this other galaxy. Now, when this becomes live, I would like you to look at the thin disk. The Milky Way has a very thin disk before. This is something like a thin pizza, which is, in particular, I think the Romans like the thin pizza. And nowadays, the Milky Way has actually a thick disk, which is more the Neapolitan or some US companies make these thick pizzas. So let's have a look at it. So this is the Milky Way before. And now it becomes live, and the stars are moving through, and they shake up the whole Milky Way. So this small fraction of stars are enough to really change the orbits of the stars in the Milky Way significantly. And if you now look at the Milky Way from the side, you see that it's becoming thicker. And in particular, we are not yet able to look at the center of the Milky Way with Gaia, because that's obscured by dust and gas clouds. But one possibility for the future is to build a near-infrared Gaia, so something which can actually penetrate gas and dust, and then we could also learn something about the bulge. We believe that this event has actually created the bulge of the Milky Way. And so galaxies like humans develop some round things in their bellies. And we also believe that this event was then feeding the black hole in the center of the Milky Way and let it grow. So this event seems to be extremely important in the history of the universe. Of the Milky Way, sorry. Now there is another very important event coming up, and that has also been done by Gaia and Hubble Space Telescope measurements. Gaia has not only looked at the stars in our own Milky Way, but also the stars of Triangulum and Andromeda. And it has for a long time, it was not clear whether Triangulum has actually already interacted with Andromeda and has created this interesting ring around Andromeda. But the Gaia data clearly show that Triangulum had never interacted with Andromeda. It will actually move this way around, while Andromeda and the Milky Way will move together. And in 4.5 billion years, they will come very close to each other. And then we don't need telescopes anymore to do extragalactic astronomy. We can just look at the sky. And so now a very important question for the future, and which will also dominate, I'm coming to this Lisa and Athena story, which will dominate some of our large missions, is what happens to these black holes which are in the center of the galaxies when these galaxies merge. Galaxy merger are very ubiquitous, and it looks like then the black holes will also somehow merge. About 15 years ago with Chandra, we looked at one of these train wrecks, one of these interaction zones, and for the first time we saw 2 active black holes in the same galaxy, and that was the remnant of this merger. And this result actually has triggered a lot of interesting studies. First, the gravitational wave folks got very happy because all of a sudden they saw indeed there are black holes which will come together. But also it was realized that already before the black holes are actually merged, they are already very bright and powerful, and they can blow away part of the gas in the galaxy, and they change completely the way the galaxies are evolving. And so let's look at a little bit how that is expected to be. So the two galaxies are crashing into each other, and then in the center, in this interaction zone, there are the two black holes which are then rumbling around in the gas, and they are happily eating, and they are growing, and the matter which is swirling into the black hole is heated up, and the last cry of help, basically, before it falls in, is radiated in X-rays and infrared and electromagnetic radiation. It takes about 100 million years for these two black holes, and then they come so close to each other that they start to lose energy by gravitational radiation, and then they shake up the space-time continuum, and they produce gravitational waves. Now, 15 years ago, we did not know how gravitational waves really look like, and so we were picturing them like waves on a pond. But now we know much better how gravitational waves look, because we have really measured them, and we have been able to do really realistic relativistic simulations. And we can even hear the gravitational waves if you are taking care. These are gravitational waves in the background, and then when the two black holes merge, you get this chirp. That is the speed of the black holes is getting so fast that it's actually chirping up. And this is what LIGO has already seen in the context of stellar mass black holes, and LISA will see in the context of supermassive black holes. So this sound in the background, what you hear is 2 years of LISA data transposed by 20 octaves so that we can hear it. And here's another one. And so the mergers, the gravitational wave mergers of these black holes are easily hearable. It's no question about signal-to-noise ratio. They will be very, very easy to find. The difficulty will be that first, it's like a microphone that you put in space, right? First you hear them, but you do not quite know where the sound comes from. And so we have to actually wait a while until LISA is then moving around the sky and then can actually pinpoint the sound from different directions and can tell us where the object is. If all of that works out, then we will be able to bring sound to the cosmic movies, in the sense that we will be able to then watch with our telescopes, with Athena, with JWST and others, the location where that merger will happen. And then we will be able to really get completely new physics that we didn't dream about 15 or 20 years before. Now, Willy has asked us a few questions, and I would like to address. I mean, I have addressed the questions about the fascination and about the big questions in astronomy, some of those that have not been addressed by others. But he in particular also has asked the question, how can young people participate in shaping the future? And this is actually what we have just started. You know that ESA is doing these long-term strategic planning exercises. And we have the hero of the Horizon 2000 exercise here, Roger Bonnet. We are right now implementing the Cosmic Vision program, and CHEOPS is actually the first Cosmic Vision mission that we implement, and LISA will be the last Cosmic Vision mission that we implemented. So we have to now think about what is the future, what is coming after Cosmic Vision, and we have called this process Voyage 2050. So it's basically trying to identify the priorities for the period 2035 to 2050. And we have done two things. We have first asked the community about their opinion, to tell us what are you dreaming about, what should be the big questions. And this social media campaign is still going on. It's still open until the end of June, and so I hope that you all convince your children to participate in that. But we have also already the first preliminary results. We have more than 10,000 people that have responded to that, and they are distributed all across Europe. We have translated this question in 10 different languages, so we even get people in Estonia, young kids in Estonia answering. In parallel, we have also started the more classical process where we ask the community for white papers, and we also have asked no, that's no gravitational wave now. We have asked the community also to self-nominate for the teams that are then selecting the priorities of the future. And this, the deadline for this process has just passed. We have gotten 218 replies, where 218 scientists have nominated or applied for joining some of these teams. It's very nice to see the age distribution on one hand. There is quite a dispersion, quite a diversity in age, but there is a clear peak around the age of 40, and there is quite a number of, half of them are younger. And it's also interesting to see, we still have a gender problem in physics and in STEM fields in general, but it's very nice to see that at least in the youngest population, the female applicants were already 40%. There is still time for you, and I hope that many of you will participate in some white papers. By the August 2019, we have the deadline for white papers for future dreams. And then we have already scheduled a workshop in Madrid in October 2019, strategically placed right in front of the ministerial meeting, which will happen in Seville, where we want to present the ideas in a similar fashion as has been done 15 years ago in the UNESCO building in Paris when we talked about cosmic vision. And then I will address, and this is in the last minute, sorry, I will address the last question that Willy has said, namely, how can we prove that what we are doing is actually having some influence on society? I mean, or how can we convince society that it's worth funding us? And this actually, I would like to show you this pyramid of innovation and value added, which has originally been put together by Sam Ting in CERN, so it's also a nice handover to the next speakers then. What is shown here on this axis is a length scale which starts with 1 meter, the classical physics where human things are happening, mechanics, thermodynamics, optics, electromagnetism, and time is moving on along the flanks of the pyramid. The black things are fundamental research results, and then you start turning that into applications like the steam machine, the car, photography, radio, airplane, TV, renewable energy. And then there's another fundamental question, the search for life in the universe, which is the current front, so to speak, of research. And in each of these columns, you see that black things are slowly turning into red things, so that means there are applications which are coming, like, for instance, the navigation system from relativity, Earth observation. Even the threats and the search for asteroids is an application in a sense. Space weather is coming here. On the other side here, you have nuclear things like the atom bomb, the nuclear reactor, but there are also now the kilonova results where finally we understand how the R process works and so on. So my message is that current research happens at this front here. So we have Gaia, gravitational waves, asteroids, and so on, neutrino astronomy. But while we basically broaden the base of the pyramid and the height, applications are coming back in and are taking over. And I would like to make two examples. One of them is relativity, and the other one is quantum mechanics. Relativity and quantum mechanics together today are making roughly 40 to 50% of the gross national product of the world. When you think about all the microelectronics, the transistors, the modern chemistry on one hand, if you think about agriculture, about large-scale construction, they are all dependent on these two theories, which have been kind of found in the turn of the century with Fraunhofer's lines of the solar spectrum and the Perry-Hill motion of Mercury. They were the basis for relativity and quantum mechanics. And so my message is, and if you go a little bit further back, if you look about electromagnetism, for instance, you know that Faraday was asked by the king, what are you doing there? Why do you spend so much effort in doing this? And then he said, my lord, there may be a time when you tax it. And that is basically electricity. So what I want to say is what we are working today, we don't know which of these flowers will in the end turn into something more, but who knows whether dark energy or dark matter or some of the Higgs particle will have some applications that you can tax in the future. And with this, I would like to thank you very much.
So thank you very much, Günther. We've got a time for a couple of questions, if people would like to ask.
Maybe we can switch the light
Switch
on.
the light on there. Okay. David Aaron Reich, please.
So the science with CubeSats on one hand is interesting in the Earth environment, so there are some Earth explorers. Science with CubeSat can also be interesting, for instance, when you think about the moon. There are some ideas where you use CubeSats around the moon, for instance, to do radio astronomy. In our case, there are more and more applications that we are talking about, like, for instance, this comet interceptor. There's a mothership that goes to the comet, and then it is actually releasing a number of smaller satellites. They are not CubeSats, they are small sats, so they're bigger. But so the concept of trying to go smaller and do science more efficient in certain dimensions is coming, I think, strong.
Any other questions? Yes, Roger. Of course. There was no choice, yes.
Yes. Yes, yes. I should have said this is the first mission since the Bonnet times where we said. Yes. Than the two individually. Yes. Yes, yes, yes. No, you should not, no. But I think there is a big pressure on all of ESA because in the latest, decades, things have gotten more and more complicated. You also have to say that now we are no longer purely talking about a spacecraft and the science instruments. We are also talking about a science craft where they are much more integrated. And actually one of our future proposals for the ministerial is also to put some extra money in the system so that we can help the member states providing the instruments, so that we can do early system engineering together, that we form teams together which are already working way ahead of when it becomes hot and expensive.
For the younger people here in the audience, that clearly demonstrated that even directors of science of ESA can be competitive. Are there any other questions? There's one right at the back.
Yes, indeed. Sorry, I forgot about that. So the Gaia data not only give you the radial velocity, they also give you rough spectra. And this population of stars is chemically different from the normal population of the Milky Way. So we can indeed see that this galaxy that came in had a slightly different chemical history and so on. Gaia is also finding more of these streams, but I think this one was the most visible and most exciting one. I think, if I remember correctly, but maybe we have to look it up in the paper, but I think that those stars have lower metallicity than the ones of the Milky Way.
Time for one final quick question. Doesn't seem to be the case right now. Thank you very much.
Yes.
Says you know how to switch. Thanks. Okay, you are live. No swearing.
Almost there.
Vielen Dank. Günther.
Just 10 minutes.
Super, vielen Dank. Ist das?
Okay. I think, as somebody said earlier this morning, it seems to be easier to send things to Mars than it does to get the compatibilities between Macintoshes and Windows 10. Okay, but enough of this. Let's move on to the next presentation. It will be given by Professor Thomas Zurbuchen, who's currently Associate Administrator for the Science Mission Directorate at NASA. Thomas, of course, is an old friend and has been to Bern several times over the past years. And why? Well, because he got his PhD here in 1986 from the University of Bern. Not long afterwards, he went to become Professor of Space Sciences and Aerospace Engineering at the University of Michigan in Ann Arbor. And also, I think also an interesting thing for people who are involved in looking at how we can transport things from space into industry. He was a founding director at the Center of Entrepreneurship in the College of Engineering in Michigan. And with that, Thomas, it's all yours.
Thank you so much. Well, I'm glad to be here, and it's one of the first talks I'm giving in English at this university after a while, so I'm really glad to do so. I've been sitting here, I've been with my neighbor sitting there. She's been adjusting her slides. You know, every time a slide is shown, she takes it off, and I know she may be down to -2. I've been thinking about how I could add value in this group, and what I decided to do is tell you first what I'm not going to talk about, and then of the questions that we're asked to address. What I'm not going to talk about is the prioritization of science. The question, what is the most important problem we should be focused on? A simple reason I don't want to talk about that, that's not my job. And it's really important that that's not my job. I can't speak for Europe. I'm sure if Günther was here, he would feel the same way with your experience. Sir, you feel the same way. The reason science has been so successful internationally is that the principles that we're using in science to figure out what we're going to do first are principles that are based on science, not principles based on likes. It's not the Thomas Zurbuchen, or however pronounce that in English, strategy, or the Roger Bonnet strategy. It's what what is brought together by the science community is prioritized. And so for me, that is not my job. So I don't want to talk about it. Of course, I have opinions, but that's not relevant. Well, it's as relevant as any individual opinion that's around here, because my opinion does not count more. Every once in a while, it counts more because I make a selection. And I'm going to talk about that in just what happened last night. So if I look a little bit tired, I'll tell you why. The second thing I want to talk about is not talk about in detail our challenges that relate to astrophysics missions, that kind of what are the things we should be focused on. I want to tell you what the challenges are that keep me up at night. And they're actually challenges that are at the interfaces of various disciplines and are systemic in nature. So I'll tell you a secret. I used to teach space system classes. And so basically, if you take any telescope that has ever been built in space, and I mostly know US telescope, some that look down, some that look up, some that look sideways. If you take any of those telescopes and you plot their cost as a function of diameter of the primary mirror, the cost scales to round numbers, like cost is proportional to t to the 1.8. D, the diameter, to the 1.8, which is almost like d squared, right? Plus minus 10%, which is another way of saying, if you want to have 4 times the collecting power, especially if you're excited about faint things, like Günther is, and the speaker at the beginning, exoplanets, you want to have 4 times the diameter, perhaps twice the diameter. The cost goes to the 4th or to the 16th. Now, I'll tell you, the telescope we're currently building that has a diameter of 6.5 meters is getting close to $8 billion. to build and launch. Now, some of these stories are horrible, and I'm going to tell you some about them. But the point is, one challenge we have is for many of you who are building their careers today, who will peak in their careers in 20 years, that paradigm needs to be addressed. Because we do not currently have a solution to how we build the next big telescope in space. There are similar type of things on the ground, even though they're a little bit different, the scales in space. There needs to be enormous innovation for us to go forward on the tremendous discovery path that you outlined, Günther, that was outlined before. So that's issue one I want to talk to you about. So figure it out. The second one is actually kind of sounds easy, but once you start thinking, you realize it's really hard. I can actually not think of a single problem that we're currently working on that's worthy of being called a high priority that only involves space or only involves the ground. All problems, whether they're dark energy, whether they're dark matter, whether they have to do with black holes, whether they have to do with exoplanets, will ultimately require both of these telescopes, types of approaches to work together. Now the problem is that they really have different histories and they have different policies that govern them in a way that's almost, it's easier to do something a lot smaller and less relevant than actually biting off that apple. Because many of the ground-based telescopes, and they're not the same, not the ones you represent, but many of the ground-based telescopes have data policies that are similar to space telescopes 20 years ago. So data have zip codes, so they live in a place, and they have owners. We don't believe in that. We don't believe in that at all. The most productive missions that we've ever built are the Hubble Space Telescope. Hubble Space Telescope last year had close to 950 publications, 950 referee publications. Chandra, which is less expensive for us, had close to 600 publications. The only way you get there is not because some really amazing senior member of the community owns that data and gives it to their grad students. It's because you distribute it openly. If we believe in science, we believe in open access to that data. It's a problem we need to solve together. We have solved it so often between our agencies. We are very much aligned. But we need to solve it as a community, because otherwise that, as well as other kind of systemic issues like that, are becoming a problem and an inhibitor of success. It may even be that some of the missions that we may want to do are much more intrinsically related. Remember the picture that he showed of the black hole? It's an amazing story. I mean, God, I was just so amazed by how this kind of using the Earth as a telescope. Well, what we could be doing, Günther and I, is actually put some of these radio telescopes on spacecraft and extend, send one to Mars and a couple to the moon, and actually create with a big data pipeline, which we're almost there. I did the calculation. Sorry, I had my team do the calculation. We can almost do this, but it requires that we totally rethink how we do this. So that second issue needs to be solved. And the final one is that we almost have an embarrassment of riches. What happens is the only way we're going to make progress, true progress, is by being able to focus. It's the science F word, focus. What that means is you say no to good because you want to enable excellent. That is one of the hardest things to do. Many people, many organizations would rather have a little telescope with their logo on it that they can go visit during the weekends and build one publication from it, rather than having their logo together with all the other logos of organizations all over the world. Because together we can transform our understanding. Whenever somebody says, I'm showing Thomas's data, I feel good sitting there. That's what excellence looks like. When you want to tell the data of making progress in astrophysics, you have to use NASA's data. That's what we want. We don't want to hold on to that data. Use it. For God's sakes, use it. But guess what? Put your data out there, like you did with Gaia data. I can tell you, when these Gaia data came out, there were organizations that I was aware of where 100 students were sitting together and young researchers and worked for entire weekends, working day and night, trying to do what I call a hackathon of getting data out of. It's something we use in entrepreneurial type of kind of a context, get data out of that. So for me, I love that Gaia mission. It's something we couldn't do in the US. We can talk about why. But it's just incredible how this mission has worked. And, you know, it's only just starting, like you said. I'm just so glad you're doing the same, using the same paradigm. Again, how do we kill the scaling law? How do you learn how to collaborate across interfaces where currently, either by policies or histories or ownership models, we cannot do that? And the third one is, how do we amplify each other and actually create, kind of select to do the excellent as opposed to the very good we own? So those are the three things that are the challenges I would like to put in front of you. You want to peak your career in 20 years, you got to solve those, all of them. We're here because of that picture. It's because one individual was an immigrant into Switzerland, came here and basically had a crazy idea. And, you know, if you've ever talked to Johannes Geis, and I'm just so sad he's not here, he's in our minds all the time, he's in mine. You know, kind of the way Johannes Geis tried to convince you is basically he walked into your office and he kept talking until he finally gave up. It's like, okay, do it. That's what he did to the NASA people. And he created this group around here, which is my educational legacy. It's a group that you know, has taken this technology and has grown into one of the powerhouses of space research with technical expertise in a handful, perhaps even more disciplines that are in space out there, with instrument legacies that are second to none. And so for me, that I just really want to talk about that. The other picture, of course, that we already talked about is that, and of course, I wouldn't be in Switzerland if I didn't show you that picture, which is Claude Nicollier with his hands on. Both of these examples, both whether it's the Johannes Geis example or Claude Nicollier's example, are a demonstration of the fact that actual research, science, that keeps us up at night because of the excitement we have, and human exploration are not contradicting if we do it the right way. And so for us, that's what we want to do. Now, how do I go forward? And now I'm going to speak to the ones who want to peak their career in 20 years. And any one of you could give that talk a lot better than me or with your own slant. But how do we create that excellence? How do we create that leadership? Well, I'll tell you how my group does it. So basically, what we want to figure out at NASA, what are we about? Basically, so first of all, we don't want to lead a national program. We want to lead a globally interconnected program of scientific discovery that encourages innovation, positively impact people's lives, and is a source of inspiration. It encourages innovation, positively impact people's lives, and is a source of inspiration. All those elements that I just read have things that do not happen in a single discipline. For us to be leaders, whether that's at NASA, I will challenge, probably say the same in your own disciplines. Encouraging innovation requires that you bring other viewpoints in, other disciplines in, other expertise in, positively impact people's lives. The only way you're going to do that is to care about those other people's lives and actually take the knowledge that you have and turn them over to the relevant owners. You've talked about some of this tremendous benefits. There's nothing we could be doing to impact people's lives in a more positive way than doing science. But we want to be scientists who are part of our society in a direct fashion, not isolated from it, because otherwise we will fall short on those opportunities that are there. And it's a source of inspiration. The reason we want to focus on inspiration so much is because of the fact that we recognize that the best thing we could be doing is to mentor people that eclipse us. Let me tell you what I mean with that. I've been involved personally between 6 and 7 instruments. Some of them I built from scratch. Some of them I was working on here in Bern. Some of them I built one by hand, you know, with the technical expert right next to me to make sure I didn't screw up. Some of them I designed and then turned over. So I look at the people I educated, 20 PhD students right now. I mean, I stopped educating PhD students, but of those 20, they've already eclipsed me together. They've already eclipsed me. It's not because I'm pretty horrible at this. It's because together they're better than I ever was. And so for me, inspiration is not just about making people excited what we're doing. It's primarily about getting people to do better what we're doing today, tomorrow. And that's what we want to do and want to be about. So we have a mission, we have values, we focus. I talked about many of them. I just want to talk about safety. Talked about values of excellence, leadership, integrity, teamwork, and safety. I want to tell you what I mean with safety. It is absolutely necessary that our research groups are safe for everybody who's in them. If they are not safe for all of the members of our research community, we artificially cut out large fractions of our research community of potential leaders that will never get a chance. And that's not what excellence leaders do. So we're spending a lot of time on that, making sure, for example, that our missions have that character, and frankly, that we hold people accountable. That if you have environments that are not like this, I'll take your money away. That's exactly what we're setting up. So we care about that, like we care about leadership, like we care about integrity and teamwork, because together, that brings us forward. I talked about all these values, and I just want to talk to you about what I did. What I want to talk now about, how can you, as an individual, who's holding my time? Okay, give me the 10-minute before the end tag, okay? So what I want to talk about is things that I learned, some of them actually here in Bern, that best set me up for the job that I'm doing right now and so many of the science jobs. And that is to trust in a diverse team, bet on the team, to learn from mistakes, and to innovate actively. So what I'm going to do is talk about those lessons by giving you 2-3 mission stories, just so you have an idea what I mean with them. And they have all to do with what it takes to build big missions. Every one of you could tell a story that you have, I bet, that is just as strong as the ones I'm talking about here. I'll talk to you about one thing that I spent last night on, and it's a new mission that is part of our portfolio since yesterday. The day before yesterday, I called up Dr. Elizabeth Turtle, and I said, she was waiting, scared. By the way, my rule of thumb is, he who causes the damage communicates. So I talk not only to the winner, also talk to the one who does not win. In every case, at the top level, that's what I do. Talk to the PI and take the beating, if there's such a thing. In this case, I talked to her on the phone and basically said, hey, how are you doing? Your life is going to change today. It's not going to be the same for the next 10 years. What you're going to focus on is this. What this is a novel type of mission that, of course, is enabled by an international collaboration between Cassini and Huygens, ESA, and the Italian Space Agency that explored Titan, one of those ocean worlds that's out there, a really weird one. It's kind of the oil spill version of an atmosphere. There's a lot of hydrocarbons out there and molecules that when somebody sends an email to the New York Times on Mars about it, whether it's right or wrong, and it makes the news. That's what happened last week for me. By the way, it was not a press release about the methane. Somebody sent an email to the New York Times. I have no clue whether this is real data or not. And the simple reason I don't know is in science, we don't look at the first data and have a conclusion. We look at the first data, then we try to kill it again, try to kill it again and again and again. And if it still is alive, it's a solid data product. Then we talk about it. So we don't send an email to the New York Times. So I don't know. It may be that this is an enormous story we're going to see in the publication. Until then, I hold my applause. You should too. So when we're going to Titan, this is how it will look. This actually takes hours to drop with a shell and a parachute. I brought this flyer. These are 8 copter, kind of a drone type of copter with 8 turning devices. You see them with a battery, a nuclear battery, hanging from the left, because of course it needs to have its own power. It's charging a battery, and all the instruments you see in the legs are mass spectrometers. In the legs are other ways we actually bring our own neutrons, because the atmosphere is so thick that the normal cosmic rays don't go through enough, so we can't see the normal gamma ray emissions. So we have to bring our own neutrons to do that. And it's that device that we're going to build and launch in 26. It will arrive in 34. It will be really, really hard. But that's what I mean with innovate actively. This is not a selection that's based on hope. We spent a year with that community trying to really push them, trying to understand whether they can take care of any one of those 10 strong weaknesses they had. And they did. I basically thought that the chances of them making it when I selected the phase 1 was less than 50%, by a lot. But it's so cool, we need to try. If we're not doing it, who is? And so basically for us, here's the science we're going to do. Innovate actively. When we do that, it opens up new doors. It creates new science. It's something that if you want to be in this field, you want to make it in that astrophysics or whatever you do, you're going to have to either come up with crazy stuff like this or learn how to enable it. By the way, being part of a team where somebody else has the idea is just as satisfying as having the idea yourself. I can tell you, the best ideas I've ever worked on were not mine. You want to work on the best idea, not your best idea. So there's absolutely nothing wrong with following a great leader. So I want to talk about the Parker Solar Probe, and there's really two stories that I want to take with you. The first one is the story of patience. You talked about the 30 years that it took for one of those missions. Parker, standing here in the middle, is the first human that ever NASA or any type of mission has been named after while alive. I felt so strongly about it, and I'm going to make my Nobel Prize punt anyway, even though the guy isn't here anymore. I basically always say the reason he doesn't have a Nobel Prize has everything to do with the Nobel Committee and nothing with his scientific capability. Of the missions that Parker did the fundamental research on, we have something like, in the NASA portfolio, 35 missions right now that do fundamental work in X-ray, astrophysics, dynamo theory, solar wind, and so forth. We named it after him. Parker, at the age of 26, lost his job while writing that paper because it was not conventional. And only because of Chandrasekhar, who was the editor of AppJ, basically said, I cannot see anything wrong, I will publish it. I remember there's a little lesson there too. Get help. You don't have to do it by yourself. Get help. So only because of that, the paper was published, and as they say, the rest is history. This mission has flown by the sun twice, and has done so successfully. Later in September, the first data are coming out, and let me just tell you, there's a lot of dead theories by the wayside about this. There's another story that I want to talk about, and that's the story of the heat shield of the Parker Solar Probe. The only way Parker Solar Probe works is because of that team, and Betsy here, kneeling in the front, she's the lead thermal engineer of that thermal system. I remember when Parker walked in, we called it the Parker Meet Parker event. Parker the man, meet Parker, the spacecraft. And he walked in, and he spent all his time at that heat shield. That's the front plate that protects the spacecraft. And he said, how do you know it works? He wanted to know the physics of how it works. And he basically said, this is way more impressive than writing a paper. If the paper is wrong, I sit down a day later perhaps, have another good idea, and I publish it. That heat shield is wrong. We're done for decades with that mission. And so basically, it takes excellence, in-depth knowledge, excellence in your team to do the kind of stuff that we're doing. And so bet on that team. We actually shipped the spacecraft to the Cape with a lot of issues. Basically, when I shipped it to the Cape over the objection of my team. And the simple reason for that was, basically, we go to Venus, so you have to wait. If you miss it, you wait 9 months until Venus comes back. I basically felt there's a chance of close to 50% that we're not going to make it on the window that we wanted to go. But if I make the decision against the team, how can I live with myself? Perhaps I'll waste $5 million by making the wrong decision, but by making the right decision, I save $100 million. It's good to bet on the team. The team is excellent. You cannot believe how hard they worked, and they got it out there. By the way, when I made the decision to launch, with all the input from all the engineers, there was none of the weaknesses left, because they worked it to ground. That's what excellent teams do. It's not that they don't have problems. What we're doing is hard. But they work through it as a team. Bet on the team, not on the individual, on the team. I want to talk about insight. You mentioned that, Pascal, there's interesting things that don't work exactly like they should. Stand in line. There's never been an instrument I built that worked exactly like I thought it would. You always get to know the instrument you launched. You think it's the same as in the lab, and okay. The team, of course, that landed the InSight lander, and what I want to talk about is the international collaborations that are there. And I want to talk about the importance of international collaborations. The way Europe works is different than the way the US works. The reason we work together is not because we think everybody needs to work like us. If Günther starts working like us, I'm far less interested in working with him. He needs to be the best ESA. There's some things ESA can do. I just talked about Gaia. There's CERN. US cannot do that. Like that steady investment over a long time. There's very few examples of that. I talked to Thomas Stocker, who is a climate scientist here. He talked about the great environment he is in to do these kind of models and start revising them. There's some things that cost, the way money is spent here is the right way of doing the work. We need to work together because as a team we're better because we're different. That's what I mean with diversity. We're different, that's why we're working together. It's not because we want the same. You should not go compare that way. As a team, we want to be better than the sum of the parts. You learn that when you land on Mars. Landing on Mars is one of the most nerve-wracking thoughts. Basically, the way you should think about it is I sit there with two speeches. One of them is thin. That's the one you want to give. One of them is really thick. It's the one you never want to give. And you basically sit there and you hope. Because if you give the big speech, there's a crater that has your name on it. And the only way you make it, of course, is not because you're like a great leader sitting there. It's because of all those people who are congratulating each other, working their buns off. And I tell you, we had problems with that spacecraft. We came in long. We had to turn the spacecraft around. We did things we never wanted to do. We lost 2 of the CubeSats. During the last 24 hours, we lost both of them, one for 6 hours. Why was I confident? Somebody made a really good decision. They put me in the back of the last navigation meeting, and I saw people arguing with each other. The person next to me is the guy who landed everything on Mars that has ever worked, Gentry Lee. But he was arguing with this other person. I knew her because she was one of my students years ago. And they were arguing about something and how to interpret data. Together, they made the right decision. The reason you put diversity in a room is because you make better decisions, because when you pull on each other than if you groupthink. What is going to kill you in your career as you go forward is groupthink. Groupthink is the enemy of excellence. You want different approaches to look at this, and that's what lands you on Mars. Of course, Mars, that is a changing planet. You already talked about it. This is the slide I would have taken out if I modified it, because you already talked about it, Pascal. Tremendous breakthroughs. Mars is way more exciting than 10 years ago. It's a different world. Astrophysics is way more exciting than when I was here. Don't listen to these talks and think they all solved all the problems. Hell no, in 20 years you need to come up with new problems. 20 years ago, these things that we're talking about, I would have bet that they would never happen. The fact that you can image a black hole, it's like a baseball on the moon. You can't image that. There's no such thing. You can. The fact that we can do gravitational waves, I would have bet a lot of money that that will never happen. We did. The fact that we could do all these exoplanets, I would have bet that would never happen. Until '95, when the firsts were announced by our Geneva colleagues. Well, Mars is an exciting place, and frankly, this is our favorite region now, because it's a river delta on Mars that we want to go to. This is a picture that we've taken just last week. It's a picture of Mars 2020 being put together with international instruments. The French instrument was just delivered. The Spanish instrument is already there. The Pixel was just delivered if you're an aficionado of this. But the point is the team is putting it together for launch in 2020. It's not because we want to do a curiosity that Mars 2020 is a historic campaign, the first round trip to another planet. We need to make those leaps. The round trip to another planet is not something we want to do. Remember my vision statement. Not as a national program. That's not what it's about. When we make history like this, we want to do the best we can. So we're doing it internationally. We're doing it with the Europeans and perhaps others. There are 3 launches involved. One that basically drops off a launch vehicle on the surface of Mars. The other one that goes and puts a catch vehicle in orbit around Mars. And the third one is a launch, the first launch, autonomous launch off the surface of Mars. And all of them have to work together. It's the most expensive Easter egg hunt ever. All these samples that will get people to work on for decades, many decades, that are out there in a little bowl, isolated, absolutely clean, will go catch and then bring it back to Earth. And then the research starts with experiments of the type that we cannot fly in space because the experiments on the ground are 100 times better on the average in many of these and the ones we can fly in space. So we're excited about it. We're excited about taking humans out of low Earth orbit and going to the moon, not because, just like what we're celebrating, not because that's a destination. It's because a waypoint to going to deep space. What the most important thing is about our strategy is that we have learned what we want to learn as an international community in our low Earth orbits. We don't want to give it up, but we want to move beyond it. And look at this celestial neighbor of ours, the moon. It's beautiful. There's many questions that we want to ask and we want to think about. We think of the moon in the context of going beyond it because that's how we think about, that's how Johannes thought about when he did that first sail up there. It's a very good idea that has big, big, big consequences. And you want to build your career that peaks in 20 years? Those are the ideas you want to work on, not yours, the best ideas. Thank you so much.
So, thank you very much, Thomas. We have time for questions. Would somebody like to ask Thomas a question? Oh, there's one down here. Thibaut.
So, you mentioned some vision, some great vision of collaboration, and also some values, safety, things like that. How independent are you from your development on these, execution of these things, on deciding the vision for the entity or the value like safety if your government is not really on the same line with you?
Yeah. So let me just give you facts, and then we can talk about the interpretation of the facts, okay? Right now, the science program we have in the US is the biggest it has been in the last 20 years. It is $7 billion. When I came in 3 years ago, it was $5.4 billion. It's $7 billion right now in round numbers. That's just a fact. Go check it. The other fact is also the Space Policy Directive, the Presidential Space Policy Directive that tells us to go to the moon with humans, says we should do so with international and commercial collaborations and partnerships. So it's 100% aligned with this. So we're not orthogonal to it. I mean, go check. Those are the facts. So they're aligned. I have some parts on there that I'm interpreting differently than a human exploration person. I told you how I think about safety. We don't tend to launch humans. That's not what our business is. So if you're launching humans, safety means something else a little bit. But other than that, those are in fact the agency values. So it's not anything that is different. So we are aligned.
A question. Roger? Yeah.
So this leads me to the next point, which is I hear from the United States in particular, and also from China, that they want to go back to the root of industrial, commercial reasons. At some point, there will be a competition between doing science of the moon and commercial, taking rocks and finding precious stones and so on. Is there a reflection that NASA about the compatibility between these two aspects, commercial development and scientific development?
So at this moment in time, you ask us.
Okay, yeah, I was just about to do that, just a second.
Go for it.
Okay, the basic question was about comparing what are the trade-off between industrial commercialization of the moon against science. This is the basic question behind it.
So those traits, whenever we explore, occur. They occur in low Earth orbit. They occur at the moon. They occur when we go and visit new shores in times past. They occur. The way we have done it at NASA, and so far, of course, like, you know the US process as well as I do, but the way we have done it as an agency is by recognizing that science drives science, and we look for opportunity, but we do not trade those things against each other. Ultimately, years in the future, there may be traits that are necessary or opportunities that are available. First of all, we are not the Department of Commerce, right? I mean, the Department of Commerce is a different animal than NASA, so kind of the ultimate commercialization, it's actually not our job. But there are traits which have occurred in the space station early on, and you know, you could go, the historian should tell us whether we got it right during the early time of the space station. I would argue we do a lot more science now because we figured out things that we can benefit from each other in a way that we didn't initially predict. And so I'm sure whenever you learn and innovate like this, there's growing pains. I would not be surprised if this is different.
Is there any other questions? Yes, there's one down here, please.
You mentioned the Parker probe, and next February the solar orbiter will be launched from the Cape. Is this just a repetition of what the Parker probe does, or do they differ, or are they complementary?
So I'm going to answer, and then Günther could say what he wants to say because it's his mission. The way I think about there's actually 3 missions that we're doing. One of them is Parker. It flies through as close as we possibly can through the through the solar atmosphere, up to 2 solar radii from the center. So, you know, if you take a football field, I shoot plots. So not that you think of the wrong football, and you go back 4 meters from the goal. That's where it is, kind of in ratio relative to the Earth. So that's what Parker is about. It's really encountering the near corona. What Solar Orbiter is about is actually about 2 objectives that are really complementary. The first one is, yes, it goes in, but it goes in with instruments that are way more sophisticated than the instruments on Parker. And the simple reason for that, we cannot afford putting the sophisticated instruments on Parker because it has to be slim, take a lot of fuel with it. So it's much simpler instrument. Way more sophisticated, this only goes into a fraction of that. What is the periapsis? 0.3. The other thing that it's doing is actually using Venus to crank up the inclination. So we actually see kind of the, if you want, the Sisley view of the North Pole. So it's not, you know, polar, but you have a chance with a telescope to look kind of over it. There's actually a lot of things at the polar regions of the sun that relate to the dynamo, the way the solar activity cycle works, as well as other questions that we just really don't know. We have never gotten any constraints from, and we want to do that. The third one, just for completeness, is actually a ground-based observatory. It's an observatory called DKIST. It's a US observatory with some European contributions as well. That's in Hawaii. And it's the first observatory to measure magnetic fields in the corona, in the low corona. Together, those 3 will provide the best view of that interface of the corona and the heliosphere, and really understand how a star drives its stellar environment, learning it from our star. How would you have said? Okay.
One last question was down here.
Increasing signals maybe on
So there are some, again, there are some things that are facts, some things we can go, think about. Just like land and air are both domains in which we do commerce in. When nations have problems with each other, the sea as well, they become domains of war. And so it is true, and you can look, European leaders have been as vocal as have been American leaders of both parties, so this is not a single person or multiple person. It is true that there's tremendous concern that there are nation states that are not following the laws that generally have been agreed upon about weaponizing space or not. The way that narrative shapes itself in the US, that concern by the president especially, is kind of labeled Space Force. So the concern you should worry about way more than the implementation of how to do that. Whenever you think about warfare as a citizen, forget where I work and so forth, I'm concerned just in general because warfare is not one of the most positive things of that part of humanity, even though it's been part of humanity as long as we know, right? So I'm concerned. In terms of science, what's the element? It's there, just like submarines are in the sea. Does it affect, if you do research? Yeah, if you're an ocean scientist, there's opportunities that come from that, but is it really an essential part? I don't know. You need to make that decision based on your own research. I think that the discussion is, make sure you understand the context of the discussion, because I think that is a context that is worth having a discussion on, and really thinking about how, as a Earth that brings more and more people into space, how we create standards of behavior in which we actually do not turn space into a zone for warfare, but we actually keep space kind of off our plate that way, just like we did with the Antarctic, in which we basically say, we're not going to do that. So if I had a wish, that's what we would do. Remember, I'm not the most powerful person in that discussion.
Great. I think we'll have to move on. Thank you very much indeed, Thomas.
Thanks.
That's good.
The pointer. Yeah. I use my finger.
Okay. Well, you have to dab it with your finger, unfortunately. Okay. Let's move on. Okay, good. We'll try and find a slide changer when we can. There's a pointer, but we need a slide changer, but thanks. We've got a pointer. Okay, we'll move on. I'd now... Seem to work. Okay, I'd now like to introduce Professor Eckhard Elsen, who's currently Director of Research and Computing at CERN, just down the road. And just by way of introduction, I'd just like to say he obtained his doctorate at Hamburg University in 1981, became a senior scientist at the DAISY Synchrotron Research Center in 1990, and was called to be Professor of Physics at Hamburg University in 2006. He's also was in charge of the LHC Experiments Committee from 2011 through to 2014. And I think he's now going to present the CERN view. Eckhard.
Well, is there a CERN view? I will try and make a long stretch, not out into the far distance, but also the contrary, on a logarithmic scale, take you to the smallest elements. And I try to sketch this view a little bit, having both the cosmos and the accelerators that we use at CERN. Those are not the biggest and most powerful ones. Indeed, the cosmic ray particles are accelerated in a way much more powerful than we currently can reach in the lab. And you have this scale here. The vertical scale is somewhat distorted here with an e-square factor just to make it more readable. But you see the particles that are impinging on Earth are far more energetic than we have reached in the lab over the past 50 years or so. And even the LHC entered here with 2 data points is not the most powerful accelerator in the world. So why don't we just copy what Cosmos does? Well, there's a problem of distance because the mechanisms which at least partly understood in through plasma acceleration and shock waves with using tremendous electric fields with high current densities and focusing the beams with magnetic fields are extended over distances that we can only dream of. So what can we reach in the lab? Well, we are more modest. It's a 27-kilometer ring, the LHC in Geneva, in the area. And we are using the energy quite efficiently by sending the particles around again and again through the electric field to accelerate them. To keep them on track, we need this technology marvel, the LHC cryo dipole, which is in fact 2 dipoles with opposite field that keep the counter-circulating protons on their track of 27 kilometers. And by the way, when they pass through this tunnel, they pass the French-Swiss border several times without paying taxes, which is unfortunate for us because we can make a living out of them. So these are the key numbers for the LHC: 7 TeV per beam, 14 TeV center of mass, and that led to the entry of the data point there. Just quickly introducing CERN from a scientific point of view, the LHC is the end element of the food chain. In fact, most of the protons that originate from the LINAC-2 here and go through a booster and then through the old PS, the oldest synchrotron that is at CERN, into the SPS built in the 70s, and then finally injected into the LHC. This happens every 10 hours or so. The other protons are used, for example, to make antiprotons here on the target. So you have to accelerate the protons up to 7 GeV or so, and then generate artificially antiprotons, which you then purposely slow down. You cool them so that you can do atomic spectroscopy on trapped antiprotons or even trapped antimatter. So this AD, the antiproton decelerator ring, is actually a workhorse for atomic physics and fundamental physics experiments, trying to see whether there's any difference in matter and antimatter, which can be detected by precision laser experiments, for example. And then there's a large share of protons going to generate neutrons on a specific target, and one can do dedicated neutron-induced experiments on that path. And then there's still some protons left which enter the SPS, can be accelerated to 400 GeV, and then we do fixed target experiments in the dedicated area, or use them for accelerated technologies that might come to bear in 10 or 20 years. Plasma wake field accelerator, which is sort of the mechanism I mentioned that the cosmos uses to accelerate particles. So this is basically the elements of the accelerators used at CERN, but I will not speak about that. I will briefly introduce you into the jargon, into the thinking in the standard model. this is the periodic table of the standard model. We could do with just the first column. Protons and neutrons are made up of up and down quarks, and they are orbited by an electron. So this first generation almost would do. Well, we need a binding force. The binding forces, the carriers of those are in this column here. The gluon, the glue between the quarks, the photons mediating electromagnetic interactions, and the Z boson and Ws as the part responsible for weak decays. These forces are unified since quite a while. So this is the static view of the model, and it was sort of completed with the discovery of the Higgs boson in 2012, which you may have heard of, and which also led to the Nobel Prize for Higgs en Anglaire in 2013. Theoretician that predicted the existence of that missing element in the standard model some 50 years ago. I will dwell on the Higgs particle. So you look at the two zeros here. It's actually the only fundamental scalar particle, so carrying no intrinsic angular momentum that we have, and that leads to quite interesting properties. This standard model has been tested in and out. I show this plot here, and I'm sure you can't read the detailed scales here. Down here, you have various interactions of particles. We start with protons here. We end up with Z bosons, Higgs, top quarks, you name it. But what is more important is maybe a cross-section, which is sort of a probability of particles interacting, varies over 15 orders of magnitude. And the unfortunate, as a scientist say, the unfortunate part is that the data points are well described by the theoretical expectations. Of course, we look for deviations to detect new physics, but so far this matches out very well, and this holds also the various center of mass energies. So this is the situation. The standard model is utterly successful, and at least for the current level of accuracy that we have reached. The elements I mentioned already, the standard model has the strong interaction, which is this alpha strong, the coupling constant responsible for that. And then the electromagnetic and the weak interactions, the electroweak theory, which is characterized by these two constants. And you notice when I say constant, in fact, it's something that varies with energy. The higher the energy, the weaker the coupling becomes for the strong interactions, and you have slightly different effects here. Now, for a long time, when the LHC turned on, there was the idea that the so-called supersymmetry would kick in to have actually these three forces join at one point in of resolution, of one point in energy, so that we would come to a grand unified theory. That is still not excluded, but so far we haven't found this missing, how to fill this missing gap so that we can really speak of a grand unified theory. So let's see what comes out of that. That is still work in progress. But what is really not solved is the role of gravitation. It is not consistently as a quantum field theory that can be incorporated here, so the dashes here are completely speculative. On the other hand, and we had this mentioned already, we have also a standard model for the evolution of the cosmos, which was established. I think the first big discovery was the observation of the microwave background, which really supported then the Big Bang picture, so the origin of the universe. And then I show this picture simply to indicate what progress is made once you improve the resolution. And we've talked about these experiments a long time. In the 90s, in fact, you basically see no structure following that initial observation of this background hiss. With the WMAP experiments in the early 2000s, you could see some more structure, and then Planck came and actually resolved this to much better accuracy. And of course, there may be follow-up now with the Euclid. So this anisotropy was completely studied, and this is the picture that we've seen earlier. It's actually the structures here that lead us to assume that there was actually the Big Bang, that created this, this picture. Let me speak a little more about the gravity, and I show this picture of the discovery of the gravitational waves because it's so important to understand that these are actually waves. They can be seen, they can be recorded. We heard the hiss earlier on. We also saw the merger of neutron stars detected. The masses are given here. And in fact, we also have the chemical analysis that was already discussed. This is maybe not the latest catalog of gravitational objects merging, starting from giant black holes, 30 times or so the solar mass, to really small neutron stars or asymmetric configuration. So this is now a new view onto the cosmos by looking into gravitational waves, and we have to take this into account not only at these wavelengths, but really also at much smaller wavelengths to understand the origin. These are, I show some of the gravitational wave detectors here simply to indicate their size. These are several kilometer legs that you need because it really, length helps actually to improve signal over noise a lot. And these are the instruments that the two interferometer installations in the US, complemented by the Virgo installation in Italy, and soon to come online, the first cold at cryogenic temperatures operated mirror with the Kagra in Japan. So this is basically the state of the art, but there's, as you know, there's talking about the next generation, the Einstein telescope, that will help resolve this. And this brings me actually to this picture. And in earlier presentations, well, we've been talking about space a lot. This is where we are today. And the various instruments, both on Earth and in space, telling us about the structure of the universe. And we also had the story of evolution from here through the various eras where nuclei formed of different composition. It started with a Big Bang, and this is where we had only quarks and gluons, the forces interacting between the component at an incredible density or temperature, rather. So this is, if there was a grand, or if there is a grand unified theory, this is where it rained and the couplings were adequate. We also talked about this wall at about 380 million years, before which we had basically the ions around, so no photons would emerge from that, and the footprint that we saw in the Planck picture is actually stemming from this era. So it's fresh, it's right after birth, but it's already 380 million years after the Big Bang. So how can we get to that period itself? And the only thing that comes to help is really by creating those conditions artificially in the lab. And this is what the LHC is about. Here's a ruler of 60 orders in magnitude. We are sitting somewhere here in the middle. If you go smaller, this is where the density of the Big Bang was. We can't quite get there, but with the LHC, we collide protons at 14 TeV, so very hot temperatures, close to distances of 10 to the minus 16, 10 to the minus 19 centimeters or so. So this is where we try to recreate the conditions, and then using the forces or the understanding of the forces we have at that time, we calculate further on and then have it evolve. At some point, the objects are so distant that strong and electromagnetic interactions no longer have an influence, and gravity takes over, and the rest we heard already of the formation of the universe. So this is pictures that we've seen over this today from the Hubble Space Telescope, actually showing us the structure. This is the spiral galaxies, which have been studied a lot, and despite of the excellent standard model that seems to describe everything, it fails dramatically. And this is one of the reasons here when you look at the velocity distributions around rotating galaxies, you think that the outer parts actually move slower. Well, we all know this when sitting on a carousel. We better do that. So this is the expected distribution, but when you actually do the measurements from various sources, you find that the velocity out there at the far distance from the center is much larger. And the only explanation we have at hand, at least conventionally, is to say that there is dark matter. In other words, mass that is gravitationally active but does not interact with light, with other particles, and so on. So there's a strong indication, in fact, when looking at the WMAP or Planck pictures in further detail, when it comes to, to this pie chart, where we are here, just 5% of what we have understood. Here we put a label against dark matter, some 23% or so. And the rest, well, I have to say again, we don't have a clue. It's the dark energy is just a name for what for the one term that Einstein introduced into his equation of general relativity. It's there. It's pushing everything outside, but what it actually is not clear. I will not speak about this much, but I will spend some more time on the dark matter because we really would like to understand. We think if there is dark matter, it should be a carrier. There should be some particle attached to it. What is it? So there are several attempts to measure it, and of course, for obvious reasons, I picked one in space already. In fact, the AMS experiment is a particle detector in the way we use it at CERN that collects spectra of charged particles in an outer orbit around the Earth. And this is one spectrum that has been recorded over the past few years, and it shows the spectrum of positrons in the composition of charged particles. The interesting part is that when you go to higher energy, you see an increase here, and this has been confirmed also by the Fermi LET satellite independently, but with larger error bars. Now, what is the reason for this increase? It's clearly not established in any way, but at least one could speculate if dark matter is out there and it's actually moving with a certain velocity, you may have dark matter particles colliding. They annihilate completely, and they might generate E plus E minus pairs. So you have an extra source of positrons, and that may be recorded. So in order to establish this, of course, you would like to see a turnover here at the other side because it's a limited mass that is available in the center of mass. So one needs more data to that. And the other part is a whole host of experiments that is carried out using so-called axions. Axions are elements that appear in field theories, but it could be that these axions actually carry a mass. One particular interesting part is where an axion actually couples to a photon, and this wild picture here is shown to indicate a photon exposed to a magnetic field B, also perpendicular to that, and using that magnetic field, it may turn in this axion particle, which then doesn't interact with anything because it would belong to this dark sector, so it would propagate through a wall. And then you do the same trick again. You plant a magnetic field, and if you're lucky, it converts again into a photon. So it's an experiment that can be carried out. You can do this with a laser and actually do a light shining through the wall experiment. You can also assume that the sun itself does this because there are enough magnetic fields. So the sun should be able to do the same thing if that were a mechanism that is realized in nature. And so you look at the particles from the sun, so you follow the sun, and actually you see this rail here on a half circle or an arc to do this. And for those of you familiar with CERN, this is one of the blue dipoles that otherwise bends the proton around the LHC ring. So these experiments can be done, and some limits have been put here. There are some experiments proposed to improve this limit, but the actual theory band goes to much smaller couplings here into that sector. And so it's still an area where we need to increase sensitivity a lot, apart from maybe this area which we can already exclude. So where else could one find dark matter? And clearly the LHC is also an example, and I've sketched here some diagrams in which one assumes a minimum coupling between our world, where we see each other and we carry masses, and this dark sector. So there might be a mediator that actually couples into that world with a faint coupling, and you can try to establish the size of this coupling or put limits on the coupling if you do see something. The advantage of doing it this way is you can generate fairly high masses through the collisions at the LHC and see whether something comes out. Unfortunately, the plots typically look like this. This is not with the full statistics, but the data points actually agree pretty well with what we expect from the standard model. And this goes out onto recoil masses of a TeV or so, and it simply looks into the recoil because in this part you wouldn't see the particles itself. So one looks into the missing mass spectra. So what else could we do? Let me come back to the Higgs particle. The Higgs particle, as I said in the beginning, is a very special particle since it carries no spin, no intrinsic angular momentum. It's a scalar particle. And while it was led to the Nobel Prize in 2013, today it has become a tool, and you can see the development from the discovery, where you had to use some imagination to actually recognize this as a signal, to what is recorded today with multiply increased statistics as a clear signal sticking out at 125 GeV. So this particle can now be used and in its decay modes to actually also to couple maybe to new physics. So is that true? This is where we stand, and I told you in the beginning the Higgs particle is special because it couples to the mass of particles. The heavier, the stronger the coupling is. And on a logarithmic scale, you have here the particle mass, and here you have the coupling of that particle to the Higgs itself, normalized in some convenient fashion. And you see that actually the particles that we know of today, the fundamental particles, here is the top quark. We start with the heaviest, the strongest coupling, the most copious production rate. We start with the heaviest, then we have the Z boson, the W boson. The B quark is also a heavy quark, top, and then so on. The precision today is still rather modest. You see, this is the scale of 50% error, so there is room for new physics to hide. This is the reason why, in fact, we want to move on, and the goal, this is sort of the goal for 2035, to reach precision of this kind, where you don't see the error bar. Well, you see it here, and we are talking percent. Why are we talking percent precision in this measurement? Isn't this over the top? No. From at least several theories, we know that sort of a precision of 1% in this quantity measured is in the range of some 10 TeV mass scale that we are exploring in the theory. So it is quite important to use that as an indicator. Now, how do we do this and collect more luminosity? We will, in fact, upgrade the LHC to the high luminosity LHC. The price to pay is that not two single protons collide, but in fact, during a collision, we will have up to 200 protons finding each other and all creating a vertex. And this is the mess of vertices that all have to be distinguished and in fact can be distinguished. Fortunately enough, most of the other collisions are just soft background. We are interested in the hard collisions that actually carry, hopefully, new physics. but it shows the experimental condition. This is the schedule. We are in fact now in a shutdown period, 2019-2020. This is when the LHC started, run 1, run 2. And the big installation for the experiments will happen in 24-25, and the machine will also then be ready to stronger focus the beam so that we get the higher interaction rate. So if we want to move beyond that scale, and it's not clear that the sensitivity of the high luminosity LHC will suffice, we are actually discussing a future circular collider, which would put us close to the end of this spectrum, of the cosmic spectrum then, and we would compete with the strongest accelerators that we can take note of, because this cutoff actually is a cutoff for propagation of charged particles through space in a very serious way. So what it takes to go to the future circular collider is in fact the elements of this, going to new magnets of 11 Tesla here. This is the one we will use now. 16 Tesla for the future circular collider. And this is a proposal for a machine of 100-kilometer length. This is the LHC, pretty small in comparison. It would still be in the Geneva area. It will go under the Lake Geneva, and it would allow to place 16 Tesla magnets to facilitate 100 TeV proton-proton collision. This is one of the elements that is discussed in our strategy discussion, which we are currently undergoing. The other element to go to high energies is with electrons and positrons in a linear fashion. Linear collider, where you use the bunches only once and dispose of them, which allows you to focus them even stronger. This is a so-called CLIC project, which is along the extent of the Lake Geneva on the French side, essentially. These are the two flagship projects that we are discussing in our strategy. Here, just a picture that shows that the sighting is possible, the terrain is sufficiently rigid, which is what you want. And this is a picture of this E+ E- linear collider, which actually uses a high-power, low-energy drive beam to transfer the electromagnetic fields onto the high-energy beam that needs to be accelerated. So the process for updating the strategy is something that has, meanwhile, quite a transition in particle physics, and it's a community-driven effort. Every 5 to 7 years or so, this is the cycle in which you have major new input. The community gets together and discusses the elements of a strategy update. The next update will be issued in May 2020. And we had a very successful meeting in Granada just a few weeks ago. And where, in fact, through physics discussion, consensus was reached on the need for a precision measurement of the Higgs particle because of its special coupling. And the route to that is, well, of course, exploiting the high luminosity LHC, doing precision measurements with E+, E-, and then reach out to the highest energy. And I should add, there are many more new ideas, but they are of smaller extent, and so that just completes the progress. The CERN Council, as the European presentation of particle physics, then signs off eventually. Before ending, let me flash a few elements of CERN knowledge transfer, which I think are particularly relevant also for the missions we discussed earlier. One is really doing irradiation tests, which we strongly need to do to see whether the electronics we are using in the tunnel are radiation hard and withstand the levels of interactions that we have. And this facility with the various facets, you can read it here, is actually also needed for space exploration to qualify electronics that goes out there, spends years in space, and is clearly exposed to high radiation. The other elements are, in fact, technologies that come about. I mentioned the radiation-hard electronic devices. This is radiation-hard electronics for power distribution. You have DC converters all over the place to adapt the sensitivity levels appropriately. This is an in-chip cooling element that is integrated, where the cooling pipes are integrated into the circuit itself, and typically it's CO2 cooling, two-phase cooling that comes about. High temperature superconducting magnets are, of course, very convenient to carry large currents needed in dedicated applications without having to go to helium temperatures. And then something that came about or comes about more and more is really monolithic active pixel detectors. So these are some 10, 20 micron side-by-side sensors that then have an active readout integrated into the chip, so that one can really do the zero suppression on the chip and read out. So this is coming as a development in collaboration with chip industry. One of the representative which is used in many space missions already is the so-called Medipix chip, which is a box that comes with a USB port if you wish, and you plug in and you do radiation measurements, and you can tell even the particle species. And then, of course, it's clear data handling in massive amounts at the level of exabyte now is one of the key themes at CERN. And this is, of course, made available to those who wish. It's here I mentioned the CERN VM file system as one of the successful elements of that. Quick chart of space missions in which CERN is actually implied with small instruments. AMS I mentioned already. This is a detector that has been designed and calibrated, built and calibrated at CERN in test beams. The control center, physics control center, is at CERN for this mission, and it's attached to the ISS, and you see the picture here. And then there's a whole suite of experiments in which CERN is also implied through the testing of circuitry. And we had already the LISA mentioned. The LISA Pathfinder has been concluded and confirms that the experiment is feasible. So we're looking forward to that happening. And Euclid I mentioned already. So this is, in fact, the institutional collaboration that we have with various institutes. And it's clear when we're talking large-scale experiments, those contexts easily come about. So instead of a summary, let me simply say this bottom-up process in which the community comes about to propose the next suite of experiments or facilities has proven to be extremely successful. The process is very active these days because on the one hand we have this standard model which is so utterly successful, but it's also so ugly that we know that there is more physics. It's almost something that a physicist cannot tolerate. You know that you're missing some important part, and what is it? And we are looking for this, and we are clearly open to new ideas here to help us really decide what is the next best instrument. We're trying to cover the phase space in the best possible way, and I try to give you some ideas about this. The process, I think, is very healthy. What is also very healthy, and Thomas mentioned this, is the international aspect. We have a very clear sharing of the tours across the globe, those where CERN is best, those where the States is best. Some activities happen in Japan. So there's a good sharing. We are not doubling the facilities. It's simply to cover all bases and come forward. Let me close with these words.
So, thank you very much. Are there any questions right now? Oh, yes, sorry.
So you mentioned the Einstein transfer of the gravitational wave. Is that the kind of project that CERN also consider as part of its portfolio?
It's a recurring question.
The
And a
question
good
was
reason
about, excuse me, ma'am. The question was about the Einstein telescope and its relation, whether CERN could participate in that.
Yeah, we just had a bigger conference, and at that occasion, the Einstein telescope was called an accelerator without particles inside. And the reason is it will require tunnels, it will require massive vacuum, it will require cryogenics. These are all talents that are available at CERN. So clearly CERN will help to consult with this. Now, frankly, I think that field is so successful, they should come with 2 suitcases full of money, and then it's trivial.
Okay, any other questions? Don't forget that if someone looks as if they're collapsing, please just hold them up. Okay, one question for Roger down here.
This was a very interesting presentation. One of the last slides that you showed was the international cooperation. It was showed a slide on which the land page, which is from China.
Yes.
Why is not China on your slide? The second question, what are the rest of things in the land emissions which you think are absolutely important?
Yeah.
Question was about collaboration with China in the first instance.
Yeah, so the collaboration with China is very loose. There are Chinese scientists taking part in the experiments. These are young students, I think like everywhere, all universities, they come. These are excellent scientists. We are in the process of concluding more formal agreements with them to really have good sharing. I must say it's also very interesting. There's good competition with the Chinese project, so they are also thinking of a huge ring in which they could, well, they would start with electron and positrons because this is where they have expertise. So the idea is what I find encouraging is that quite different to a few years ago, they are now interested in fundamental science. So that this is a good sign, and it really bore fruit already with the Daya Bay experiments, where they were the first to actually establish some neutrino mixing with high precision. So that is good. On the other hand, we feel it's a bit, the exchange is more in one direction. And this is clearly something we have to work on. It's quite different to other collaborations where well, this is really on equal footing. So we have to see how this goes about. When I speak of the strategy, there's a European strategy and there's similar activities in the US and in Asia. Those groups have representative in our strategy, European strategy process, so the input will be absorbed, but they are then prepared to develop their own strategy. On the dumper, I cannot say very much. Here the main element is we have the status of recognized experiments at CERN. So these are scientists that may wish to have beam time at CERN or use the context of CERN to theorists or some particular detector knowledge. So we allow them to work at CERN for a limited period. It's a minor impact on the CERN activity itself, but it fosters the exchange, and at this level, the interaction happens.
Okay, great. Thank you very much again, and it's time to move on.
Start putting all of these up.
Careful, it is live.
All right. Oops.
Voilà.
Takes about 20 seconds to go live. Is my All right.
Okay, very good. Okay. One more wave. Okay. And I'd like to introduce our last speaker for the symposium today. It's Ewine van Dishoeck. She's Professor of Molecular Astrophysics at Leiden Observatory in the Netherlands. Leiden is a place I know very well. I spent a lot of time very, very drunk there when I worked for the agency. She's currently, however, President of the International Astronomical Union. And I think it's fair to say she's one of the pioneers of astrochemistry. And she's received numerous awards, far too many to mention here. But most recently, the James Craig Watson Medal of the US National Academy of Sciences. And so, Ewine, it's all yours.
All right, good afternoon, everybody. I think we have been gradually warming up during the day. We're now probably at the hottest part of the day. Thank you very much for sticking out here in the heat. I'm trying to bring you back to sort of some of the coolest places of the universe, where it's just barely above absolute zero, although that won't help us much in this particular room. Okay, so I'm standing here actually both as the president of the IAU and also as somebody interested in astrochemistry, star and planet formation. So I'm going to talk about both of these aspects. I'm going to start by saying a few words about the IAU. One of the questions, what does your organization do? And then I'll dive into some of the science, and then at the end I'll come back also to the IAU and how the two of them actually come together. So the IAU is basically the organization of all the professional astronomers worldwide, and this happens to be a very special year for us because we're celebrating that we were founded 100 years ago. And we're using this opportunity actually to have lots of activities across the world celebrating not just the IAU, but really celebrating a century of astronomical progress and what it has brought to society in terms of technology and cultural impact. And of course, you've seen already quite a bit of that here during the day. In fact, if you just think back of 1990, what we knew then, it was so little, we didn't even know where the elements in our body come from. The progress has been enormous, but has been in all of these aspects, and they have really gone together. So the IAU is basically, its mission is to promote and safeguard astronomy in all of its aspects. And it does that through international cooperation. So really working together is going to be a key part of this story, both from the IAU side, but also from the scientific side. And from the IAU side, that means these days so much more than just research. Of course, we have lots of scientific meetings, we have general assemblies, we have symposia, but these days we also put a lot more effort into communication. We have an Office of Astronomy outreach in Japan. We are starting a new office on astronomy education, and we have a very successful office on astronomy for development. We have by now some 13,500 members from more than 100 different nationalities, and we have 82 member countries. So you can see the challenge already in working together with so many different nationality. We have increasing diversity, not just in terms of the female fraction, but also diversity, of course, in terms of the nationalities. And also we have now junior members. And in fact, the co-chair of our junior member working group, Maria Drosowskaya, she is actually here at Bern. So she is going to be key in leading sort of this effort over the next year from the IAU point of view. So I mentioned we're celebrating our 100 years. We have lots of activities over the globe, but we have sort of two central themes. Among the themes that we're celebrating, one of them is that this is, of course, also the year of the 100 years, that it was 100 years ago that there was the solar eclipse expedition of Eddington, which basically proved general relativity. And we had wonderful events both in Sobral, in Brazil, and also Principe Island, where Eddington went just last month. And then, of course, this month is the one of the 50th anniversary of the moon landing. And we see that's being celebrated just everywhere across the globe. And in fact, it was already reminded of this wonderful experiment here that Johannes Gijs put on the Apollo 11. In fact, you see Buzz Aldrin, who I met for the first time just yesterday at Starmus, is unfolding actually this solar wind experiment. And that turned out to be also very successful scientifically. I won't have time to go into it, but there's a very interesting story also on helium-3 that came out of this experiment. And in fact, also against Switzerland in Geneva, Corinna Charbonnel has been playing a very key role in unraveling that scientific story. Okay, maybe if you could dim the lights now a little bit, if that is possible. I'm going to address one of Willy's questions, namely to us as speakers, namely what are the big questions that you're interested in. We've heard this morning already from Ryan Schmid some of the 3 biggest questions. The ones that I always like best is where do we come from, where are we going, and then obviously the one, are we alone? And all of that story of where do we come from and are we alone, that starts in the very tenuous clouds between the stars, where we actually built the first molecules, where we built the first dust particles, and ultimately that grows basically then into planets that may or may not look like our Earth, and also a moon that may or may not look like our moon. So, to address Willy's second question, namely what is sort of the broader impact of the science, we've talked a lot about the technology, and we've seen wonderful examples of the technology spin-off. But for me, the cultural impact is just as big. And you just have to look anywhere in culture. I mean, Starmus is going on in Zurich very successfully, just combining music and science. You just have to look at poetry, plenty of examples. One of my own hobbies is basically looking at astronomy and art, and you find that again, just across the entire globe. Of course, my own native Dutch Vincent van Gogh just had to paint the Starry Night. You know, he had to do that, he writes in his letters to Theo. If you go to the Aboriginals in Australia, the Milky Way dreamings, they have this beautiful southern sky above them. And they have all kinds of story about the Milky Way and how that is part, basically, of their cosmology, the Milky Way dreaming. If you go to the Pacific Northwest in Canada, there's yet another story. It's about first raven actually stealing the sun from the moon. The sun was locked up in a dark box, and it was basically by first raven put on the sky. And so that's their story. And then in German Expressionism, you find all kinds of stories and also paintings here of Kandinsky, of stars. And then, in fact, one of my favorite painters is Paul Klee, and this is one of his many nice paintings that he has, this time the cosmic composition, which is full of stars, moons, comets, etc. Good. The other part of the inspiration and the perspective, actually, that space brings. We saw already the Orion Nebula. It was shown in Günther's talk. And you just have to look here at the sky, and hopefully we'll be able to do it on one of these nights, away from the city light, on one of your beautiful mountain tops. And then you really start to realize the perspective that space actually gives us. These stars, they shine for everybody. They are not hindered by borders if you look down from space onto Earth. Even the more bigger picture is that where we are actually living here, if we now look at our own galaxy, the Milky Way, and we realize that the sun is just one of a few hundreds of billions of stars, and that we are living just on a small rocky planet around that ordinary star in a garden variety galaxy, of which there are, again, several hundred billions in the universe. So again, it provides a perspective and certainly also addresses already to some degree this question, are we alone or not? Because the sort of the big revolution that has happened since the mid-1990s with the detection of the exoplanets, and again, of course, here in Switzerland, with Michel Mayor and Didier Queloz, has put all of these age-old questions that have been with us for centuries and centuries, has put it in a completely new perspective. We now know that our planets are not the only planets in the universe, but that actually, on average, every star has at least one planet. But there are many questions over the type that they are and whether they or not they could be habitable. We now know that they come in a huge diversity of planetary systems, some of them close by, some of them far away, some of them big, some of them small, but the majority of them of a type somewhere in between Earth and Neptune, super-Earths or mini-Neptunes that we have no equivalent of in our own solar system. So these are clearly questions that we need to start addressing. And if we focus back on our own solar system, and then the billion-dollar question, or euros, or yens, is undoubtedly how were we formed some 4.5 billion years ago. And this is, of course, what Pascal already very nicely addressed in her story about studying Earth and the Moon and Mars. But we have indeed information of all kinds of messengers from our own solar system. The Rosetta mission, of course, a fantastic scientific success, probing the outer part, the cold part of our solar system in the form of comets. And then now both Hayabusa 2 and OSIRIS-REx looking at these weird-shaped asteroids and trying to probe their composition, their content, etc. And of course, we also have the meteorites that are falling on Earth on a regular basis that tell us part of the stories. And then, last not but least, the lunar rocks that the Apollo astronauts actually brought back from the moon also tell part of that story, and I'll come back to that also towards the end. Okay, so this talk is aimed at non-experts, so just to say a few words as to where stars and planets are being born. That's in these clouds of gas and dust between the stars. It's not in this very nice, colorful part of the nebula. That's very hot gas. That's more than 10,000 degrees. That's where the gas is ionized. What we are looking here is basically the atomic hydrogen recombination lines. But these stars and planets are born in these very dark regions here of the image. And you see that here, actually, as part of the Carina Nebula, where we nicely have a reflection nebula in the background so that we see these dark clouds actually as silhouettes in front of them. These are images from the Hubble Space Telescope. And you can just point your telescope at one of these dark clouds, such as you see over here, and then that is where you will find lots of molecules, and that's also where you'll find stars and planets that are forming. Now, these clouds are so dark, actually, because they contain very tiny dust grains, about 1/10 of a micron in size. They're made of silicates and carbonaceous material, and they make the clouds look dark because they absorb and scatter the light, just like the smog in the atmosphere on a day like today means that you cannot see your beautiful mountains, but you just see the dark clouds, actually, of the smog in between. These clouds are cold, some 300 degrees colder than it is in this room at this very moment, only 10 degrees above absolute zero, and the densities are very low, only about 10,000 particles per cubic centimeter. So again, to compare this with this room here, here we have 1 cubic centimeter containing about 3 times 10 to the 19 particles per cubic centimeter. And even a good vacuum in a laboratory still has of the order of, say, 100 million particles per cubic centimeter. So when an astronomer talks about a dense cloud, it is still much and much more tenuous than anything that we normally have here on Earth. These clouds are actually big, and they are several light years across, and they contain enough material to form some 10,000 new stars, although they will do that with an efficiency of only a few percent. But there's certainly lots of material available in order to make new stars. Now, this year, 2019, is also the International Year of the Periodic Table, also to celebrate Mendeleev's contributions over the last 50 years, especially in understanding the periodic table. Now, the periodic table that the chemists look at and that you've had in your high school chemistry classes certainly looks different from the one that we have as the astronomers. Hydrogen and helium, both produced in the Big Bang, are by far the most abundant. And those elements that we are interested in, carbon, nitrogen, oxygen, sulfur, we saw several times, they are present at the level of 10 to the minus 4 to 10 to the minus 5 with respect to hydrogen, so just a fraction of a promille. So we have this very cold, this very tenuous gas that is mostly hydrogen, you know, where particles may meet each other maybe only once every 10,000 or 100,000 years. And so chemists told the astronomers, don't even bother looking for molecules in space, you will not find them. Now, fortunately, the astronomers didn't listen, and they tuned to their, which is also a good lesson, never listen too much to predictions, they can be wrong. But they actually tuned their receivers, and they found one after the other molecules, and also a few examples in just a moment. One of the molecules that has been found already quite early on is water. And thanks to a lot of work, both observational with the Herschel Space Observatory and also in the laboratory, we now think we understand how most of the water in space is actually formed. And it's on these tiny dust grains. These dust grains actually act as a sort of catalyst, but not in the chemical sense, of bringing atoms together and forming a molecule here like water. So maybe once a day, a hydrogen atom lands on such a grain, it finds another particle, and then it goes off again. But it can also find an oxygen, it can make hydrogen peroxide, the intermediate ones, and then it can make here two water molecules. And now we fast forward, and we go over 10,000 years or so, and then we make a nice icy layer on our surface of our grain, and that is actually what we can also observe with our infrared telescopes, the water ice in space, and that is actually the process by which we think that most of the bonds of the water molecules were actually made in space. So when you look here at water in this glass or in your body or in one of your beautiful lakes or the snow on top of the mountains, those original bonds were made already some 4.5 billion years ago in the cloud out of which our own solar system collapsed. Of course, since that time, water has been recycled, it has condensed and has evaporated, but most of the bonds actually span from that early period. And so, as one of my colleagues said, if you think about it, actually water is older than the sun itself. Good. So, we've talked a little bit about chemistry, talk a little bit more about it, but let's first look at how we actually make a planetary system. So here's one of those dark clouds, and for a long time it can be actually stable, but at some stage it will actually start to collapse under its own weight, simply gravity taking over, and because the cloud has a little bit of initial rotation, you start to form one of these disks around the young star. And it is really these disks that are then the sites of where future planet formation can occur. Now, in order to observe these disks and in order to observe the star-forming region, we had to build a new facility. And this is what was alluded to already in several earlier talks, the Atacama Large Millimeter Array, a fantastic new telescope that was inaugurated in 2013. A few aspects that I would like to stress here, again, in this theme of collaboration. This was the first example of worldwide collaboration in astronomy, bringing together Europe with East Asia and North America to build a single facility here in northern Chile. It has been hugely successful. It was also a technological challenge and also a logistical challenge, bringing these components from all over the globe to this single spot there in northern Chile in order to integrate all of these components here at the mid-level facility at an altitude where you can still think at 3,000 meters, put them all together, test them, and then finally put them on a big truck and drive them up and then put them in the array at 5,000 meters. So, and also with receivers that are sort of at really the quantum limit of what you can have. So astronomy, again, driving engineers to the ultimate precision and that in the long run, finding then its spin-off in society. So here is what it was at that time, and now we have this beautiful array, which actually is a breathtaking experience, both literally and figuratively, if you're up there at 5,000 meters. It's truly one of the most beautiful places on Earth that I know of. Now, ALMA has taken sort of this search for components, ingredients for life to a whole new dimension, in the sense that previously we were always looking on the scale of entire clouds, like the Orion cloud. Now we're actually able to zoom in on the scales of new solar systems. So say 50 astronomical units, the size, the orbit of Neptune or the orbit of Uranus even, we can see these complex molecules now sitting there. And here's just a few examples of molecules that we have found near a solar mass star that is forming at this very moment. And you see already we go to propanol, to 3 carbon atoms from 2 carbon atoms, other interesting species, and then especially these ones. This is work from Niels Lichterink, who is actually now also in Bern here at CSH, and showing here molecules that actually have the beginning of peptide bonds, which are, of course, important for as building blocks for possible life elsewhere in the universe. In fact, amino acids have often been claimed in the literature as being detected, but so far there's no detection of even the simplest amino acids, glycine, yet. Has been seen in comets, but not yet here. So this is clearly one of these species that we'll be hunting for in the coming years. There's also plenty of alcohol in space. I think the Orion cloud already by itself has enough alcohol for some 10 to the 29 bottles of whiskey. So if you get thirsty tonight, you can just send one of the astronauts to one of these clouds. But beware, it's not 40% alcohol. It's less than 1% alcohol, actually, with respect to water in those clouds. So what I've shown you so far is that in spite of the very tenuous conditions, there is a very rich chemistry there, and it's found actually in nearly all the forming stars in the Milky Way and also on scales of new solar systems, which means that at least the ingredients, the building blocks, are plenty available throughout the Milky Way. Now, how about the building blocks for planets? Are they available? So this is again where ALMA comes in. ALMA had to be built because these disks are actually small, so on the size even of this image, one of these disks, of which you saw an artist impression, is just a tiny little spot over there, and so we really needed ALMA in order to be able to zoom in and find these places where planets are being built at this very moment. And now ALMA can do this. It can do it even remarkably quickly, at least if you're just interested in the continuum. If you're not interested in the gas, then in 1 minute in the nearby star-forming regions, ALMA can just detect all of these disks and even see their wonderful structure in there, as was shown, for example, also in the talk by Xavier Barcons. That provides us also just converting this flux that we're seeing here into amount of dust mass provides us immediately with the amount of material that is actually available. And if you then look at sort of what we found now from sort of looking at thousands of these disks, is that nearly all of the young stars are surrounded by these disks, and that on general, the masses of these disks are enough to form a solar system, at least 25% of them. For that, you need about 1% of the mass of the sun, maybe 10 times the mass of Jupiter, whereas the other 75% have at least enough material to form Earth-like planets. So in other words, the ingredients for planet formation also appear to be quite common in throughout the entire Milky Way. Now, can we actually see planets forming? And this is actually part of a rather big debate that is going on. ALMA has given us these wonderful images that you see over here. This is a disk, and we had expected to see a very smooth surface density profile, but instead we see all of these rings happening there. And one of the suggestions is actually that there is a planet there in the inner region that is carving a gap, and that is what we are seeing here is actually the lanes that have been excavated by these planets. Now, this interpretation is not uncontested. There are also other explanations for these structures that we are seeing. But one thing that is common is that at least all the bright big disks that we've looked at, they also show some sort of structure. And again, on solar system scales. We see rings, we see cavities, we see very asymmetric peanuts, we see spiral arms, here other forms of rings. And so it's really a very lively community at the moment, basically a new age of observational planet formation that is now trying to figure out what these kinds of images are actually telling us about planet formation. Oops, no sounds, no sounds, no sounds, no sounds. Please turn down the sound. No sound. Disks in which planet formation is maybe occurring. And this was basically meant to show you how you go from these tiny little dust particles that are just a fraction of a micrometer in size to something that is a lot bigger, and where you see already these interesting structures also appearing, like we see in some of the comets, where it looks like they're just two of these for new planets. So, in a nutshell, if we want to build an Earth like we have here, there are several stages to go through. We go from these tiny little dust particles that we have before to kilometer-sized bodies, planetesimals. These are really the building blocks. This is where gravity starts to take over again. Then we get to the planetary embryos, lunar or Mars size, and then eventually into something that may or may not look like Earth. But comets are clearly a very important intermediate step in this entire story. And this is where, again, the collaborations with Bern and where Bern has made such an important contribution come in, namely through the Rosetta mission, especially the Rosina instrument. Because these comets, we can see them beautifully here in Comet Hale-Bopp, and we have visited them through the Rosetta mission. And it's really this Rosina instrument that has, and especially the double focusing mass spectrometer, with all the credit going to the long-term vision of Hans Balsiger, Katrien Altweg, being a fantastic leader of the team, and now also Martin Rubin leading the efforts at Bern in sort of sniffing up all of these molecules that are coming out of this comet and seeing what is there and also what is not there. And in fact, now we are actually able to make sort of this comparison with what we see in a young disk in this very sort of early stage of planet formation with sort of one of the products or intermediate steps towards planet formation, namely in the form of comets. And very similar compositions are actually found. Going back to the Apollo 11, because that's what we're celebrating here today. That's the reason for this wonderful symposium. Just a couple of sentences and slides on what the lunar rocks have actually told us. I mean, they've certainly told us that the moon surface is ancient, and they've told us a little bit about the origin of the moon. Here you see some of the moon rocks that were brought back. In fact, if you look at the pre-Apollo stories, there were a lot of weird theories floating around on the origin of the moon. Was it captured actually by a passing body? Was it sort of spun off the young Earth when it spun too fast, or was there another theory of it? But I think what the lunar rocks have shown is that most likely, although still not uncontested, the moon was formed by a collision, actually a giant impact of, say, a Mars-sized body on the early Earth, and that then from the debris of that, that actually the moon condensed. So some of the lines of evidence are the incredible similarity in the composition that there is actually between the moon rocks and the Earth rocks. In fact, this position has only grown in the last 50 years. It's fantastic that all of these rocks were curated, that now with incredibly accurate instruments, these moon rocks can now be studied with so much more precision than was possible 50 years ago. And in fact, this has also led to a little bit of a crisis. They are almost too similar. It looks like the moon was made almost entirely from the mantle material of the Earth. So I'm sure that as new studies will be going on of these still existing moon rocks, this story will continue to unfold. It's also clear that we need rocks or sampling of different parts of the moon, and that's already happening on the backside of the moon by the Chinese, and that we also, as Pascal emphasized, we need to study Mars, asteroids, and comet material. Okay, so let me actually, in the last couple of minutes, go back to the cultural inspiration. This is an engraving that was made already in 1798, and that artist already envisaged that there was not just our solar system, but that there were lots of other solar systems. Some of them with planets closer by, some of them further away, some of them more massive, some of them less massive. And that is, of course, exactly what we find at this moment, and there are many new missions planned. We've heard about them both in space and also on the ground. The ELT is being built in order to test and study these new solar systems. It's also happening here in Bern, and I want to compliment Willy on bringing people together here in Switzerland on this particular topic through the Planet S NCR that you see so beautifully illustrated over there has really provided a focal point, bringing people together in very interesting teams in order to study these questions of exoplanets composition, but also how they were formed and what it means. And of course, CHAOPS is what we're looking forward to in unraveling part of that story. The next step is going to be to link the composition of the exoplanets that these new missions will start to form, to link that with their birthplaces. I mean, can these compositions tell us something about where they were actually formed in these disks? There's some very interesting theories how ratios of, say, carbon over oxygen actually change in where in the disks these exoplanets were formed. But an important conclusion is that we may actually be the first generation of scientists that actually have the technological capabilities in order to answer this question about are we alone and search for life elsewhere. Will it happen? We don't know. This is definitely a multidisciplinary study. As we heard also this morning, we are just doing this part of this adventure. We are just providing the conditions and the ingredients that we have in space. But then there are geological aspects, chemical aspects, biological aspects that you need to take into account to see whether or whether not life could arise on any of these other planets. We're just saying from the astronomical side, yes, it's possible. There are these ingredients, but there are a lot of other steps, and there's a whole sort of new fields on origin of life happening in chemistry and biology that are taking that then from their perspective. Okay, so we're celebrating actually a century of progress in astronomy, which has been tremendous, and what it has brought to society. And we've seen already examples of that. We're doing this from the IAU side with more than 3,000 activities in more than 100 countries. And here you see those countries illustrated. And so we're really going all over the world in order to do that. I've already mentioned that the 50-year moon landing is one of our activities. Of course, a lot of those activities are happening also stimulated in other ways, such as, for example, here in Bern, the festivities that will start actually this weekend, Bern im All. If you look at sort of the next centuries, then it's clear that our dreams, what we want to do, these big questions that we want to answer, they will require big facilities, and we really need to work together in order to make them happen, and also the big service there. And this is really also what partly unites us, and what we are trying to stimulate from the IAU point of view in order to build these connections between research groups, between countries, between facilities in order to make this possible. It is not just the facility, it's the big data, the new technologies. All of this is part of the challenges that we have to address as our field in the coming century. And in the more broader perspective with society, we are of course having the science and research part, but we definitely also have the cultural and society part, and then, as we talked about, the technology of skills part. And we are very proud of our Office of Astronomy for Development that actually tackles many of these questions in developing countries and makes that possible, and uses actually astronomy as capacity building in those regions. Okay, so let's just end with looking back at Earth. Of course, the famous Earthrise from Apollo 8 is one of those iconic images. This is another one, the pale blue dot, that tells us again that this is us, this tiny little dot far away. So again, space provides perspective, provides also some modesty, and it definitely provides tolerance. So I want to end here with a beautiful picture of this sky, and just say happy birthday and 100 years here in the 3 languages that you actually have here in Switzerland. Thank you very much.
Thank you very much, Ewine. Are there any questions to that presentation? Thomas Zurbuchen.
Could you comment on the statement that was made earlier about these satellites that SpaceX wants to launch and others? Could you just tell me, first of all, what is your organization doing? What's the timescale over which you're looking at?
Yeah.
Are there others that we should
Right, so yes, those are some of the slides that I left out, but definitely the IAU has also as its mandate to be protectors of the dark skies, and that means both visible light, but also radio. The radio quiet, that's also a very important issue. What we're doing is actually, together also with ESO and other organizations, through UNESCO, we are organizing actually a joint conference on this early next year, in which we will certainly also invite the SpaceX representatives to be there. So I think all of our organizations have come out with initial statements on not being happy about these satellite trains. Now I think we need to do a lot more modeling and quantification of the effects, and a lot of this will come together in this high-level meeting that we're having with UNESCO early next year.
Any other questions from the audience? Yes, Xavier. Oh, Roger?
Thank you very much. It's a very interesting expose. I wanted to ask you one thing concerning the moon. I am a lunar ecologist. I am very concerned about the future of our moon. There are many crazy ideas to extract helium-3 and to do a lot of things with the water, which is not so plenty. What are the actions taken by the IAU to preserve the moon as a scientific platform for the history of the moon, the history of the Earth, the history of the solar system?
The question, just say I'll repeat, the question from Roger at the front here was that what is the IAU doing to protect the moon?
Yeah, I must say at this moment we are not looking into these kinds of legal questions, so to say, because it will come down to legal issues, undoubtedly. I fully agree with you that some of these ideas that are around about mining helium-3 or water, there's really not that much water there. There's a tiny little bit there, but it's not that much. That doesn't look to be so realistic. So let's hope that also the proponents of them start to realize that they are not so realistic with that. But yeah, it is a concern. Yeah.
Well, I would like to take an opposing view, actually. I seem to recall Chris McKay when we were talking about terraforming of Mars by throwing CFCs into the atmosphere and filling the atmosphere of Mars with underarm deodorant. And he said, well, why not? We've destroyed everything else on the Earth. Why can't we go and destroy Mars as well?
I'm not sure that that is the happy note of which we want to end this conference.
You're absolutely right. I was just being awkward as usual.
Yeah.
Are there any other questions? No, if that doesn't seem to be the case. Fan yourselves and ask a question.
Yes, one comment.
Okay.
Stars belong to everybody. What about the Earth?
Yeah, all of its inhabitants. No.
Right. Okay then, thank you very much, Ewine. Thank you very much indeed. And just before we close, I'll hand the microphone across to Willie Bentz for a final couple of comments.
Okay, so with that wonderful talk, we came to the end of this symposium. I hope you got the inspiration you came looking for by attending this symposium. I certainly have one single wish left. I wish I was 20 years younger. Because apparently there will be a lot of action in the future, and I'm not quite as young as some other speakers who have said they might live the detection of life in the universe during their lifetime. So I'm trying to get some additional time here. Anyway, so now we'll round up here, and we move to the next part of the thing. But I think one more thank you for all the speakers of the day. It was difficult for them to come here. Some got delayed because of the heat. It was warm all the time. Some are between airplanes came here. So I would really like to acknowledge their willingness to come and talk to us and share with us their ideas, their visions. I know it wasn't so easy for them. Thank you very much. Okay, and now we proceed to the next part, which is the open public part, which is the action on the Bundesplatz. And so the official inauguration of the activities over there will be at 5:30. So we have, all right, so once again, we have problem, but never mind. So the official inauguration of the Bundesplatz activities will be at 5:30. So you have ample time to go from here to the Bundesplatz. You can even have time for beer on the way, probably, or at least some refreshment. Don't forget to drink enough. And then there will go on, the evening will go on. I was told that there will be some music on the Bundesplatz. There will be some things to look at. And so you can enjoy a few hours over there if it's not too hot, but then go in the shade and things like that. So thank you very much for coming. Have a good evening on the Bundesplatz, and keep tuned on space activities during the weekend and during the coming weeks and months. Thank you very much.
got your stuff.
Before they disappear again. That's one. That is my...
Possible to ask a question?
Sure, go ahead.
So, if the crash between